value. So basically, this is not a constant inductance, right? There is a variable inductance. But if this one was not here, it was just simple air gap. It doesn't matter how much current you have, how much voltage, unless you get to the saturation. You know, we assume we are not going to saturation. So L is a constant number, right? This is another thing. Go to problem number 1. I asked you to calculate the energy. 80%. They went with the volume and those kind of things. Energy is for half of the line square. Right? You know the current? And how much was the L? L squared over R. Basically, you needed only to calculate the R equal, right? Half of you, that one is correct. I'm not saying it's wrong. You went to calculate the density of the energy, time it by volume of the air gap, all those kind of things. I don't know what, you know, as simple as that. And that would be a simple, very, very short answer. You're going to see the answer later, you know. Now, let's come back to this circuit. LA, I'm going to talk about LA first. Remember, if we had two windings here, for example, let's say we had another one here, you had it in the homework already, right? We said if you want to calculate L11, what do you do? Get rid of that one, right? Get rid of that winding. Just say n to the power of 2 divided by the reluctance of the circuit from this point, right? So we're going to calculate LAA here. Let's forget all the other three windings. I'm going to talk about LAA, right? So doesn't matter where is this one, how much is the theta? I am here or here or here or here or here. Doesn't matter or not? No. So why? Because the air gap is constant, right? Because this is cylindrical, right? So air gap doesn't change. If this one even rotates, air gap is not going to change, right? But if this one was like this, see, this is the solid pole. This is a stator, and now this one, when it rotates, the air gap is going to change, right? I'm standing here looking at this air gap, right? Right now is this much. But if this one goes here, the air gap is going to get bigger and bigger, right? So it's variable. Based on the data, it's going to be variable air gap, right? But for this one, because it's a cylinder here, right? Doesn't matter where is this one. It's going to be here, 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 here. All the time the air gap is fixed. The number of turns is fixed. How much is the LAA? It's going to be NA to the power of 2, whatever term I have here, divided by the reluctance of this circuit. So basically, flux is going to go like this, right? Of phase A is going to generate the flux going this way and going this way, right? So, and it doesn't matter where is this one, right? So, what's the result of that? This LAA is a constant number. I mean, variable here is the theta, right? Doesn't matter how much is the theta. All the time, let me see, did I use the right notation or not? Yeah. So that's a constant number. How about LBB and LCC? The same thing, right? If I want to calculate LBB, let's get rid of the rest. Again, just the position of this one came here, right? For LCC, just came here, right? They are also fixed. How about LAA and LBB and LCC? What? And assume all three phases they have the same number of terms. They're the same, right? Because it's going to be n to the power of 2 divided by reluctance, right? For all of them, the reluctance is the same because it doesn't matter if you're standing here or standing here or standing here, air gap is the same everywhere, right? Reluctance is the same. If the number of turns also are the same, so all of them are going to be the same. Basically, we'll say this. Let's call this one LA. Give me the name LA, right? This LAA has two parts. Go back to the transformer part, you know. We had a flux coming here, right? A little bit of this one also is going to go here, right? We have two inductance. There was the magnetic inductance and the leakage inductance, right? The same thing here. So some of this one is going to go through the magnet, some of it is going through air, right? So basically, we're going to call it LA0 plus LAL. This is the leakage. This is from the leakage flux. This is from the magnetic flux, right? You remember all these things, right? We talked about this one in the transformer. We talked about this one in the inductance when we talked about it. So this is a magnetic inductance. And this is a leakage. So we have a leakage flux, and we have, see, I'm saying the concept is exactly like transformer we have. We had a magnetic flux, we had a leakage flux, right? Magnetic flux is going to generate the magnetic inductance, and we have a leakage flux which is going to generate the leakage inductance, right? So we know now what the LAA, LBB, LCC, and LAA, LBB, LCC, right? That one is clear. Now we are going to go to the next one. Is going to be LFF. Let's look at LFF. Forget all these three. How about the self-inductance of LFF? Variable. I mean, variable. What's variable based on what? The theta, right? How much is the theta? Theta 0, theta 10, theta 20, theta 15, theta. Is it a function of theta or not? No. Why? Because whatever the air here, again, the air gap is the same, right? As soon as the air gap is the same, because number of turns cannot change, right? So that in self-inductance is going to be a constant number, right? So basically, LFF also is a constant number. And again, this one is going to be LFF 0 plus LFL. Again, part of it is a magnetic flux, part of it is a leakage flux, right? Now, we'll get to the mutual inductance. That's a nice part. Yes.
I'm having trouble imagining the air gap. From where in the diagram is that?
This is the air gap, yeah. See, I didn't, see, basically if I'm going to complete this one, I should, put this one. These are iron. These are iron and this is the air gap.
Okay.
So in every motor you open, you see there is a one part is moving, right? It cannot be attached to the stator because if it's attached, it cannot move, right? There is a small, see here I'm exaggerating, I put a huge air gap here. But air gap usually is like 1 millimeter, 2 millimeter, something like that. It's very, very small. Why? Can you tell me why the air gap usually is very, very small? Maybe, but not that. Better. Huh? Yes. Better than that. We say you want to have a high torque, high force. What do you want? High, very big magnet, right? Very strong magnet, right? What does it mean, a strong magnet? More flux, right? Bigger flux, right? So if I put big air gap here, flux is Ni over R, right? R is proportional to the air gap, right? If I put a big air gap here, the reluctance is pretty big, right? So the flux is going to be very small, right? So we minimize the air gap because we're going to get a stronger movement. But what's the problem with making it very small? Manufacturing, mechanical part. If somehow there is a little bit thing, boom, it's going to hit the stator, the motor is gone, right? You have to make sure you have enough tolerance at any speed. You're not going to hit the stator, right? So you can make it 5 millimeter to be very comfortable, but that one is going to hit you from the other side. Your torque is going to come down, right? So this is a very important part. You have to design this one correctly. The smaller air gap, the better, because you're going to get a higher torque for the same current and voltage you're putting in the machine. Same number of turns and current and voltage. The smaller air gap, the better, but you have a limitation because of the mechanical design and those kinds of things. I'm talking too much now because I want to get this one to somewhere. Now, the next one, what we have, see this one, they are clear. These are all clear, right? And we know these are like the same, right? I should put this one out here. LAF is LFA, right? LBF is LFB. LCF is LFC, right? These are the same. So basically, half of this matrix also is gone. So we need just to clear the top part, right? If we know how much we are. Now let's start with the easy one. LAB and LBC. You need a little bit of imagination here. Let me explain it here with a simple circuit, you understand it. So, going back again to homework, I think number 2, I think added in homework number 2 or number 1. You said we have a system like this, for example. One winding here and another one here, right? How we did calculate the lambda L12 or L21? We said lambda 1 is L11 I1 plus L12 I2, and lambda 2 is going to be L21 or L11 I1 plus L22 I2. This one very clear how we're going to calculate this one, right? You know how to calculate L11 and L22. How to calculate L12? We said L12 is going to be lambda 1 over I2 when I1 is how much? 0, right? Basically, it's saying how much linkage, not leakage, linkage we have between these two flux. For example, this one is generating phi2, right? It said how much of this phi2 is going through this one, right? So part of it, this one is going to come here, part of it is going to go here, right? The one is going to help you to calculate L12 is this part, right? Because lambda 1, in this case, is going to be this flux times this number of terms, right? So basically, how much these two, they are correlated with each other, right? Now look at here. I have a phase A, flux is like this. I have a phase B, flux is like this, and I have phase C, like that. How much these two are correlated? Huh? Correlation of this one and this one, right? That's the correlation of these two, right? It's going to be something cosine of 120 degree, right? How about this two? It's going to be cosine 120, right? Cosine of 120, right? And because these three windings are exactly the same, current, number of terms, everything is the same. So basically, all of them are going to be the same number, right? Basically, LAB is going to be equal to LBA, is going to be to LCA, LAC to LBC equal to L, what else? CB. And how much? Something cosine 120, right? What do you call it? Something? Let me see. Oh, I know what you mean. It's going to be, again, this one I have to go explain. LAA0 cosine of 120. How much is the cosine of 120? Minus 1 over 2, right? Only I need to explain why I put LA0, right? It's going to be something cosine of 120, right? I want to say why the something is the LA0. I'm going to go back here. I'm going to go back again here because it's easier to explain it here. If this one is N1 and this is N2, right? If you calculate it, the self-inductance of this one is N1 to the power root of 2 over R, right? If you calculate this one, sorry, this is a self, LL1, this one. L12 or L21, if you calculate it, it's going to be N1 times N2. I'm not sure how many of you can remember this one. It's going to be N1, N2 divided R, right? Let's call this one LA0. Well, I call it over there, right? For phase A, right? So, in this transformer, if these two, they are N1 moves, right? Let's say this is N1 turn and this one is N1 turn also, right? How much is this? Right? LA0, right? In this transformer, rotating transformer, NA, NB, and NC, they are all the same, right? If you look at it, LA0, where did I put it? It's going to be NA to the power of 2 divided by R, right? But because NB and NC, they are the same, for all of them, it's going to, let's say, call it N to the power of 2 over R, right? How about the mutual inductance? It's going to be something NA times NB over R, right? But because NA and NB, they are again both, so basically it's like LA0. So that's the reason I put here also LA0. Same thing I put it here. The same thing I put it here, right? Leakage inductance is very good question. See, when we calculate this one, leakage inductance is going to stay here. It stay here, right? It's not going to go through this one. So the part is going through this one is calculated. So that's the reason just I use this one. I didn't use this one. This one is not going to go to the other one, right? This one is going to stay for each winding. It's not going to go over there. I'm trying to explain it very simple, with a simple language, you know, how we are going to, we are almost there, you know. We are almost there, the difficult part almost we are finishing, you know. So we now we know the, what's the LC, this one is known, this one is known, and now the last one is this one, right? They are going to go to the one they have a letter A, B, C, and F, right? If I can figure out that one, I'm done. I can write everything down and just simplify this equation and get to where we are. Okay, let me write this one. So you know where this comes. 120 is the projection of this flux on each other, right? How much they are correlated together, right? And cosine of 120 is going to show that one. And LA0 is coming because both windings, they have the same number of turns. Now, the next one is going to be this one. Okay. We're almost there. Now, LAF. How much is the LAF? Again, we have this one, the number of turns is not as same as NA, NB, NC. NA, NB, NC, they are the same. And for example, is N. This one, the number of turns is NF. It could be a different number, right? First of all, let's forget the other two, right? Let's forget the other two. I'm going to look at only A and F. So the mutual inductance between these two is again correlate with the flux. How much they have correlation, right? Like here we said 120. Look at here. So if I am here, the correlation is projection of this one and this one, right? Let's say this one goes over. It will come to 90 degrees. How much is the projection? 0, right? If it is 0, it's completely correlated, 100% correlated, right? If I go here, it is different. So what does it mean? It's a function of theta, right? It's not a constant number. It's going to change based on where is the theta, right? So it's going to be LAF, but times cosine theta, right? Cosine theta. How about LAF? Again, LAF is going to relate to the number of turns of phase A, number of turns of field winding F, and the reluctance of this circuit, right? Which is the air gap. Now I'm going to go through LBF. Guys, tell me how much is LBF? And LC. You tell me. LAF. And this one? Why did we say LAF for all of them? First of all, those three, they have the same number of ones, right? We said this one depends to what? Depends to the NA, right? NF and the gap you are seeing, right? Gap is not going to change. It's not a function of theta, whatever. Because it's cylindrical, it makes our life easy, right? So for this one, it's going to be depending to what? LBF. Let's call this one LBF. It's going to be NB